Okay, so all right, so it's the first semester, or first seminar semester. So we'll be given by our Neil Banik, right? So Neil started his postdoc here a mere, let's call it 5 months ago, ish.
Yeah.
So he got his PhD from the University of Florida, working on axions and effective axions in astrophysics and cosmology. Let's see, I think he did one of those studentships at Fermilab, yeah, right? Caitlin, hey Caitlin, did you just go back from this? Very good. So then you got into topics in cosmology and galactic dynamics, and took a postdoc primarily at Leiden, which is in the Netherlands, and he did a lot of work while he was there at the Gravitational Institute. I always forget what the acronym stands for, but it's something to do with particle activity cosmology.
Something like that.
So while he was there, he picked up working on stellar streams and using stellar streams as probes, as astrophysical probes of dark matter. So now he's sort of, past few years, he's turned into one of the world's experts in using stellar streams and all the really awesome data that's coming in these days on them to probe properties of dark matter and galaxy formation. So, and he's going to talk to us today about that topic. And that's it. So, good work.
Okay, well, thank you, Louis. So I'll be talking about stellar streams and how we can use that for a bunch of those to detect dark matter substructures and constrain the microphysics of dark matter. So the plan of the talk is as follows. I'll go over the basic Lambda-CDM framework, which predicts that a Milky Way-sized host halo should have several thousands or even hundreds of thousands of dark matter substructures. And then I will introduce what exactly are stellar streams and how density gaps form in stellar streams, and what can we learn from these gaps. And then finally, I'm going to talk about, instead of looking at individual gaps, what we can study in a statistical way from the power spectrum of stream density, and how we can use that power spectrum to distinguish between cold and warm dark matter. I will talk about this big uncertainty which comes from the baryonic structures in our galaxy and how they can also perturb the streams and mimic these gaps. And then finally, I'll talk about how I use the data on GD1 from Gaia and PanSTARRS combined with the slow-one data on PAL5 to constrain the particle nature of dark matter. I also look at the classical satellites, and so this talk will be based on these 4 papers. So our understanding of the universe is somewhat precise yet incomplete. Precise in the sense that we have some idea that all the structures that we see, like galaxies and galaxy cluster, comprises of only 5% of the energy budget. The remaining 75% is completely unknown. Oh, sorry, the remaining 95% is completely unknown. 70% is what is called the dark energy, which is responsible for the accelerated expansion of the universe. And the remaining 27% is dark matter, which has mass, has gravity, but we have no idea what it is. This is the general consensus. I know there are other models in which we talk about modified Newtonian dynamics, but in this talk we're not going to talk about that. I can give some brief overview after this talk and how these observations kind of put a final nail to the coffin in our mind, but at the moment we're not going to talk about that. So I'm going to show this animation from the Aquarius simulation, in which it shows how structures form from the initial density fluctuations left over after inflation. So this is a dark matter only simulation. The brighter colors indicate higher density, and this is a Milky Way sized host halo. And what it shows is that small clusters form first, and then they merge to form bigger structures. So in this model, at the end, and this is today, inside a Milky Way sized host halo, you can see that there are numerous small scale structures. And these are what we call subhalos or substructures. So inside a Milky Way sized host halo, in the fiducial CDM model, we should predict that there are hundreds of thousands of these structures, some as massive as 10 to the 9, solar mass or even more. These acid structures, which are above 10 to the 9 or so, they should be able to make the star formation, essentially, I guess, as dwarf galaxies. These are the known dwarf galaxies of our Milky Way. But the low mass subhalos should be devoid of stars because they don't have enough gravity to initiate star formation. And so detecting these low mass subhalos is the main aim of this topic. So the next question that comes up is, why are we so interested in these low mass subhalos? And there are two reasons. The first is it will teach us about the clustering at subgalactic scale, which we still don't really know. And the second, it will tell us a great deal about the particle nature of dark matter, because the microphysics or the model parameters of dark matter dictates this lower mass bound of the subhalos. So here I'm showing the linear atom power spectrum for different mass of dark matter. The black solid line is the fiducial CDM model. So it goes all the way to very low mass subhalos, showing that in the CDM, you should expect very low mass subhalos, even as low as moon mass or sun mass subhalos. But as you decrease the mass of the dark matter, so I don't have a pointer, but as you decrease the mass, the power spectrum has a cutoff at certain scales. So what this shows is that if you decrease the mass, you become more warm. That is, the velocity dispersion of the dark matter particles increase. And so it washes out structures below a certain mass scale. And this is what is, this is the basic picture from the Aquarius simulation from Hubble and others, where it shows that in the warm dark matter, there are no tiny substructures or below a certain mass scale. So as you go very low mass, so for example, when you get like a KV or so, then you don't have any substructures below like 10 to the 10 solar mass or 10 to the 9 solar mass. But to give you an idea, if dark matter is a 3.3 keV from a relic, then the minimum subhalo mass should be 10 to the 8 solar mass. So if you're able to detect a subhalo, say 10 to the 6 solar mass, then you can rule out a 3.3 keV model with very high significance. Okay, so there are two methods to detect these very low mass subhalos. One of them is the strong gravitational lensing. So you can study the flux anomalies from distant quasars by, and how they are perturbed by these subhalos via gravitational lensing. And the only other method that we have at the moment is the stellar streams. So stellar streams form when a globular cluster or a dwarf galaxy falls into the Milky Way potential and is tidally disrupted by the gravity of the galaxy. So this green blob falls into the Milky Way and it's tidally disrupted, sort of spaghettified into the stellar stream. And what this shows is that if you have, let's say, it also depends on the orbit of this initial object. So that's the stellar stream that we're talking about. So this is the final product. So depending on the orbit and the initial mass of the object, we can expect various lengths of the stream. And we see several streams in the sky. For example, this is from the slow one, and so it shows 4 of the most popular streams. The GD1 stream is a globular cluster. The PAL5 still attached to the PAL5 of the cluster, which is the progenitor. These two are globular cluster streams, so their velocity dispersion is very low, and that's why they're thin and long. Whereas the orphan stream is most likely a dwarf galaxy stream, is much wider, and the Sagittarius, of course, it's a messy dwarf galaxy stream, still in the process of being stripped from its progenitor. We have discovered several more streams with dark energy survey, and many more with Gaia. So there is a whole arsenal of stellar streams in our galaxy to be explored. So the stream density is largely uniform along the stream until it encounters a perturber. Could be a subhalo, could be a baryonic structures. But what happens is when a mass flies past the stream, it kicks the member stars. And as a result, these member stars will then be on different orbit. And over the course of its evolution, it will fly off and it will result in a density gap or a region of very low stellar density. So to understand this, I'm going to show this animation. So in both these animations, we are at the center of mass frame of the stream. The top one is the unperturbed stream, and the bottom panel shows the perturbed stream by two subhalos. So observe how the gaps appear over the course of its evolution. So that's the first impact. And if you compare, there's a gap and it's evolving in time. And that's the second impact. And at the end, you can see there's a clear gap compared to the unperturbed stream. And so these are the gaps that we're interested in studying and exploring and using to constrain subhalo properties. And we do see such gaps. So this is the GD1 stream from Gaia and PanSTARRS. And you can clearly see these gaps and the associated surface density falls at the location of the gaps. And these gaps are most likely due to subhalos, given the orbit of the GD1. It's far separated from all the baryonic junk in the galaxy, which is enclosing the disk and closer to the galactic center. And so, we're going to come back to this topic later, in which I'm going to constrain that the GD1 can actually tell us about how abundant the darkness and structures are. So, if you just look at the individual gap size, it does tell a lot about the perturber, because the gap size is caused by the perturber, so it depends on the mass, the velocity of flyby, time of impact, the size of the perturber. And so if you just take the individual gaps and do an MCMC analysis, you can constrain several of the properties, such as impact parameter, time of impact, scale radius, or the size. But there's an important degeneracy between the velocity of flyby and the mass of the subhalo or the perturber. And this degeneracy is almost impossible to break with the current level of noise in the data. So to demonstrate this in a more visual way, here this is a simulated stream density, and these are the gaps caused by three different kinds of impacts. And if you see, the gap size is the same, even for three very different kinds of impact. And so future data may allow us to measure the depth of the gap, but for the current level of noise that we have in the data, it's pretty much impossible to distinguish between these three different perturbers. And so, this also does not tell us about the subhalo population that we're talking about. It only tells us about the individual perturber that may have impacted the stream. So an alternate way to look at this problem is to give up the idea that we need to just study individual gaps. So what we're going to do is, instead of asking what can a single gap size tell us, we're going to study the total stellar density and study it in a statistical way. So what we're going to do is, we're going to simulate the stream density, and we're going to impact it with a population of subhalos. But then we're going to marginalize over the subhalo velocities, mass, time of impact, and all the other different impact parameters. So if we study several, thousands of such realizations, we should be able to compute the power spectrum of these densities. So what I'm showing here is that a single stream, which had impacts in a fiducial CDM model by several different realizations of subhalos. And if we compute the Fourier transform of the stream density, we get the power spectrum. So the x-axis is basically the angular scale along the stream, and the y-axis is the power at those scales. And the gray shaded region is a dispersion in power due to the various different kinds of impacts that the stream has. So let's look at how we can use this power spectrum of the stream density to study subhalos. So this is one example that I'm showing. So in each of these cases, the stream had impacts by a single mass subhalo. So each of these lines is the median power spectrum from 1,000 different realizations of subhalo impact and for different axes. So one way, the first way, the first thing that we see from these plots is that if a stream had impacts from a very low mass subhalo, then you have more power at smaller angular scale. Well, this makes sense because lower mass subhalos are smaller, and so they should impart small scale perturbations over the stream. And higher mass subhalos should be able to impact the stream over a bigger or longer angular scales, which should impart power at larger scales. So here I'm showing the power spectrum in the density, and there's a track, which is the second angle or the transverse angle of the stream. And this is the cross between density and track. And so in all these three different kinds of power, you see the same features. That is, smaller subhalos will impart power at smaller angular scales, and bigger or more massive subhalos will impart power over larger angular scales. So we're going to use this this observation to see if we can distinguish between different models of subhalos. So to refresh our memory on cold and warm dark matter, warm dark matter is associated with higher velocity dispersion. So it's sort of washed out structures below a certain mass scale. And so statistically, in a warm dark matter, a stream should have fewer subhalo impacts than in a cold dark matter case. So the way we model warm dark matter is through this transfer function, which relates the power spectrum in the cold dark matter. So this is a linear kind of power spectrum in the cold dark matter, and that's in the warm dark matter. Alpha consists of this cutoff scales, which depend on the mass of the dark matter here, and that dictates the scale at which the power spectrum will have the cutoff. And so, if you have lower mass dark matter, the cutoff will shift to the left, or small scale structures will be washed out. And this can be generalized to fancier dark matter models like sterile neutrinos, but the overall physics and observations will not change. Okay, next we need is a subhalo mass function to sample subhalos for our simulations. So for the cold dark matter, we use the mass function obtained from simulation, such as the Aquarius, where the slope of the mass function has minus 1.9, and we assume for the radial distribution of these subhalos to have an ionicity profile. In the same way, for the warm dark matter, we get this fit from the Apostle simulations. And this fit has this half-mode mass, which basically tells us the mass below which there will be no substructures in a certain model. Okay, so we have these two ingredients, including dark matter subhalos of a certain model in the simulations. So next we need to simulate these. So we did the simulations, and these are the results for the power spectrum in different model of dark matter. So if you have a very warm dark matter, like 5 kV, then this is the power spectrum. So this is the median of thousands of different realizations of the stream densities. So again, we see a same feature, that is the overall amplitude is less in warm dark matter because there are fewer substructures. And for cold dark matter, the overall amplitude is higher. And also there is no power at small scale in the warm dark matter, whereas in the cold dark matter, you have power. So the next step is to see if we can use these power spectrum to distinguish between models of dark matter. Because there was a clear trend in the power spectrum of density between different models of dark matter. So to do that, we use this likelihood-free approach called the approximate Bayesian combination approach, which is essentially a fancy term for saying that we're going to run several thousands of simulations over the prior range and pick only those simulations which are close to the observation. If they are close to the observation, we take them and we construct a posterior from those simulations. That's all. So we did that on a test case. So these are the two different test cases. So in this case, we took a stream that was evolved in a 5 kV warm dark matter universe. And in this case, it was a cold dark matter universe. And then we run the ABC machine, and this is the posterior. So we get a peak close to the 5 kV, so we get a peak at 5 And in this case, we don't see a peak because the peak is all the way off because it's at 1 G. So the peak plateau is showing that the predicted value is beyond the range of the fire. So this gives us confidence that this method works. And so we're going to try to use this method on actual observations. Okay, any questions at this point?
Okay, what did you assume for the input for the properties of the stream? Like its magnitude, its density, its width, so forth. Does that play a role here?
Yeah, so we do need the age of the stream, the progenitor, and the dynamic range. So for that, we have to model the stream based on where the progenitor is, and the orbit.
So did you have in mind a particular GD1 or something like this?
Yeah.
So this is basically based on GD1.
This is a very mock GD1.
Okay.
Yeah. I'm going to talk about the real GD1 later. Okay. Any other? Okay. So far I did not assume the perturbations from the baryonic structures. So this is a big uncertainty. For example, if you look at, in particular, the case of PAL5, it has a lot of density variations that you can see here. Because it passes to the disk several times over its dynamical evolution. So then, given this density, can we confidently attribute all these density variations to subhalos? So that's the question we're going to ask and see if we can actually do that. So PAL5 will be perturbed, or in general, any stream in our galaxy will be perturbed by these 4 different kinds of structures. The galactic bar, spiral arms, we don't actually know if it's 2 or 4, so we have to test the models. The entire population of the giant molecular clouds and other public clusters. So all these 4 can perturb the stream. And we did this analysis. We computed the power spectrum in all these 4 different cases, and this is the result. So the black dots are the power of the observed PAL5. The gray horizontal line is the noise in the data. And these powers of each of these individual cases show how much power you can expect from each of these individual perturbers. So in this case, we can see that for the galactic bar and the GMCs can individually account for the power that we observe for PAL5. And also the spiral arms can impart enough power to account for the power that could have happened from the CDM substructures. So the PAL5 is highly perturbed by all these structures. And so it's a poor role for dark matter substructures. So when dealing with streams, we have to be very careful in picking a good stream, like a GD1, as opposed to the PAL5. But then later I'll show that we can combine PAL5 data with GD1 to constrain dark matter. Okay, So Cal 5 is not that great, but what about G1? So G1 is this thin long stream, and then with recent data, we were able to extract around 120 degrees of this stream. So what can we say from this stream? Okay, so the first uncertainty for the G1 is that we have no idea where the progenitor is, and we also don't know how old the G1 is. So some hope came from this paper by Jeremy Webb and Joe Bovee, in which they said that the progenitor is most likely between -30 to -45, and it most likely disrupted around 500 million years ago and caused a gap. So a gap because when the final stars were ejected, there was a gap. And so because we see a gap at -40 degrees, which is this, so this is what we assume the possible location of the progenitor of E1 is. But then there are other gaps too, like -20 degrees, and if you compare these models to the observation, you can see that even at -20 degrees, the stream sort of has a good match. So we do this analysis even considering the progenitor to be at -20 degrees. The results did not vary at all, because the difference in age between a G1, which has a progenitor at -40 versus a -20, is only 30 million years. And this is too short of a time to make any change in the actual results. So I'm just going to show all the results after this based on the fiducial model, which considers the progenitor to be at -40 degrees. So the next thing is the age. So in Webb and Bovee's model, they consider the age to be 3.4 gigayears. But if you look at the stream, there are several regions along the stream, especially if you look at the stream between -32 to -12, the average width is as low as 6 arc minutes. And because the stream width is proportional to the velocity dispersion of the stars, and the stream length is proportional to the velocity dispersion times dynamical age, you can then do a very quick calculation and say that the stream could have been much older, in which case the stream will be much thinner. And all the thicker regions along the stream is due to heating due to either subhalos or background structures. So the stream could be as old as 7 gigayears, in which case the width will be 5.7 arc minutes, close to the width that we observed. And so there is no way to tell whether it's only 3.4 gigayears or 7 gigayears. So in our analysis, what we did was we considered all kinds of stream models between 3 and 7 gigayears. And we basically marginalized over all these ages. So then let's see how much perturbations the baryonic structures alone can impart onto the G1 stream. So we ran all these effects of the baryonic structure, that is VAR, GMC, spiral arms, and the 11 clusters on the G1, and this is the result. This does not have any CDM subhalos yet. These are the data power for the leading and the trailing arm, and these are the power in the simulated streams. The blue one is for a 7 gigayear old model. The red one is for 5, and the black is 3 gigayears. And the shaded region is a 2 sigma dispersion in power for the 7 gigayear old model. And even with 2 sigma, you see that there is no way you can account for the observed density power that we see on G1 for the trailing as well as the leading. So what this indicates is that G1 has to be perturbed by something more than the baryonic structure that we see. And as I showed previously from the orbit, it strongly suggests that it has to be due to subhalos. So if we add CDM subhalos, this is the power that we see. So this has the effects of all the baryonic structures and a fiducial population of CDM subhalos. And with that, you can easily account for the observed power. The dispersion happens, again, this is because we don't know where the subhalo would have hit. And the dispersion is because we marginalize over the velocity of flyby, time of impact, impact parameters, and all these things. Because there's no way to know how the subhalos could have impacted the stream. Okay, so we know that if we add CDM subhalos, we can account for the observed power. So let's try to quantify the amount of substructures that we can, in the stream. So we ran the ABC machine again on the G1, PAL5, and then on combined G1 and PAL5. So what we're trying to do here is we're trying to constrain the subhalo abundance in the mass range 10 to the 5 to 10 to the 9 solar mass. The prior that we considered is a log uniform between -1.5 and 1. For the GD1, we consider all these ages because we have no idea how old the GD1 is. And these are the results. So the blue posterior here shows if we only consider the GD1 stream, and it has a peak at 0.7. And it puts an upper limit of 2.7. So by 0.7, I mean 0.7 times the subhalo abundance predicted by the fiducial GD1 model. And then this 2D plot shows the how older models of G1 prefers a lower subhalo abundance than a younger one. And this is because from this plot you can see that older G1 models will have more power. This is because if a stream is going around in the galaxy for a longer period of time, then it will have more impacts with subhalos and dynamic structures. And so it will require less subhalo abundance compared to a younger G1 model. And so that's from only the G1. From only PAL5 is the red PDF, which only puts an upper limit of 0.9 at 95% confidence. And it doesn't have a peak as expected because PAL5 is already heavily perturbed by the baryonic structures. It only requires very low subhalo abundance to account for the observed power. If we combine these two, then we get a peak at 0.4 and an upper bound of 0.9 at 95%. So this looks kind of weird because we are expecting very low subhalo abundance. But it is important to note that the fiducial CDM model that we consider doesn't have any subhalo disruption by disk or any other baryonic structures. And the expected subhalo disruption is around 50 to 60% or even higher, as we know from the recent fire simulations. And so these results are actually consistent with cosmological simulations. And if future surveys, such as the European Observatory, can tell us more about the age of the G1, then we should be able to constrain or put tighter constraints on the subhalo abundance on the G1. Okay, so that's for the overall subhalo abundance in the entire aspin. Next, we're going to look at how these streams can, or what these streams can tell us about the subhalo abundance in each of the mass decades. So we considered 4 mass decades, 10 to the 5 to 6, 6 to 7, 7 to 8, and 8 to 9. The main reason is that subhalo disruption is most likely mass dependent. That is, more massive subhalos will be more likely to disrupt. So we individually vary the subhalo abundance, apply the ABC machine, and these are the results. I'm not showing the case for 10 to the 5 to 10 to the 6 because the posterior were just flat, because these are too low subhalo mass, and our streams with the current level of data are not sensitive to that level of subhalo mass. For the 6 to 7, we only obtain an upper bound on the subhalo abundance, and for the other 2 higher mass bins, we obtain peaks as well as an upper bound. So let's see if we can use these measurements to constrain the dark matter mass. Okay, so But let's start by plotting everything and all the results that we obtained. So these are the measurements of the 3 mass bins that we obtained. I'm only showing the upper mass bound for the 6 to 7 because that's what we obtained. These are for the 7 to 8 and 8 to 9. The black solid line is the fiducial mass function for the CDM model. The gray region is the CDM mass function considering 2 to 10 times disruption of subhalos as predicted by cosmological simulations. And then I've also added the part from the classical nuclear satellites in order to extend our study above 10 to the 9 solar mass. The error bars here are the percentage platforms. And so these are, the overall measurement that we have at the moment for all these subhalo mass bins. So now the idea is to see if we can obtain a best fit, or for all these measurements. So to obtain the best fit, we consider a maximum likelihood approach. Our likelihood has 2 parts, one of the stellar stream, the other for the classical nuclear satellites. Then we have the amplitude of the mass function. We consider a log uniform Breyer between 0.01 to 100, so very conservative Breyer. The slope is between minus 1.95 to minus 1.85, and this comes from the Aquarius simulations. This is the same range of slope that was used by the strong gravitational density community to constrain dark matter recently. The mass of the dark matter we consider a log uniform in the half-mole mass, also inspired by the strong gravitational density community. And then we also added a fraction of subhalos that will survive this disk disruption. So this is also an overall normalization that multiplies the subhalo mass function in our model. And we consider, again, a very conservative bound on the F survive to be between 0.1 to 50%. So the first thing that we find is that F survive is around 20%, which is, again, consistent with cosmological simulations. And for that amount of subhalo disruption, we can then plot several models of dark matter. So these are for the 3 kV, 6, and all the way to 20 kV. And then we try to ask which model is the best fit for all these data. And we obtain an upper bound of the half-mole mass to be 4.2 times 10 to the 7 at 95%, which translates to the mass of dark matter to be at least 6.3 kV at 95%. This is a kV higher than the strong gravitational and using the same wires. So this is, I think, I should say this because this is so far the strongest constraints on the dark matter.
I think I lost something. How do you define F survive?
F survive is just a term which multiplies the overall subhalo mass function. So
this is supposed to account for like disk effects?
Disk effects and all the other background effects.
Okay, so basically, I survive parentheses in the presence of baryons, which was not included in Aquarius. Because the original subhalo mass function model comes from Aquarius.
Yes.
Which is dark matter.
Yes.
And then you need to correct that.
Yes, exactly.
Okay.
Exactly. Yes.
Okay. And
so yeah, so this is the so far up to the strongest constraints on dark matter, right? And so in conclusion, I would say stellar streams provide a very strong way to detect dark matter substructures and also constrain their abundance. Ionic structures can also perturb these streams, and so we can't simply take a stream and start applying it on dark matter models, especially if a stream is higher this, it's very far away from the galactic center at the present time. It doesn't mean that that stream did not go through the disk in its orbital evolution. And so the first step in any of these studies is to actually orbit model a stream and see if it actually went through the disk or anywhere close to the galactic center. And then based on that, we can use that stream to constrain the dark matter substructures. We can use this statistical analysis that I presented here to constrain the dark matter substructure. So far, we have used GD1 and PAL5, but we are obtaining more data with several other surveys, such as S5. So we should be able to model many more stellar streams, combine those statistics, and obtain more robust constraints on dark matter. And then finally, this is so far the strongest constraints, and let's see how long it stays like that on the particle dark matter. So these are all sort of the past research that I did. The future is to look at different models of dark matter, self-interacting dark matter, and ultralight axion-like particles in particular. So I've been looking at the Sagittarius stream and how we can use that to constrain self-interacting dark matter because Sagittarius is a high dark matter content object, so it will tell us whether scattering cross-section of self-interacting dark matter is angle dependent